Hello, class. Okay, so we're going to continue discussing Newton's second law of motion and focus on how we actually use this law. For more than, we've done some very simple problems, but it's kind of a general procedure that we can use to apply Newton's second law to a given problem. So first, I'll just write down the steps. I'm going to write it over here, and then I guess we'll erase it later. But I guess the order at first doesn't matter too much, but one thing we definitely want to do is identify all forces acting on every object in the system. So we've looked at applying Newton's second law to just like an object, but we could have multiple objects in our system. One example we're going to consider is something like this. A very kind of standard problem. But say you have a cart, tie a string to it, have the string go over a pulley, and it's tied to a hanging mast. And you release it, and so there's two objects in our system. So in order to use Newton's second law here, this is bothering me, let's support that. Okay. So we'd have to identify all the forces acting on each mass in the system. And again, you could say there's three objects, the string too, but we're considering the string as something that just transmits forces without any losses. Actually, when we get to chapter 9, we'll learn that the pulley itself can play a part. Because if we were doing this, you could have like a fixed pulley where the string just slides over it, but then friction can be significant. But really what we'd rather have is a spinning pulley. And that spinning pulley is definitely a part of the system, but we're going to ignore that for now. And actually it's usually not that significant anyways, but we'll learn how we could take that into account. Not until we get to chapter 9 though. So anyways, your system can be more than just a single object. And you have to apply you have to identify all the forces acting on each object in the system. So I should have just drawn this over here for now. So I'll redraw it. I'm going to rename these. I'm going to call these M1 and M2. Now, step 2, take a coordinate system or systems. Okay, now there's two factors you want to consider when it comes to picking coordinate systems. By far the most important one is the motion of the objects in question. Let me do a variation of this picture off to the side. Let's do the first two steps, but let's say we have a problem like this, where we have a cart on an inclined plane. Let's call that M1, and again, that's attached to a pulley, and here's M2. Okay, so step 1, identify all forces acting on every object in the system. This is actually not quite as easy as it looks. But let's start with the easy one, M2. We'd have gravity and tension upwards. So we have gravity and tension. And then for this mass on the incline, we have gravity, which is straight down. We have tension, pulling the mass this way. We have a normal force. And the reason I said that this problem isn't quite as easy as it might look at first, just identifying the forces, is we have friction. But at this point, we don't actually know where friction is going to go. Like, what direction is it? Because if M1 is massive, it's going to fall down the incline and pick up mass 2 with it. It depends on the relative masses, M1 and M2, and also the slope of the incline. If it's a steeper slope and M1's bigger, it's going to win. And so we have to determine what direction this thing wants to move without friction. And once we do that, then we can determine how to add friction to it. But I put wheels on it so we can ignore friction. So, you know what, this picture is the same as this one, except we have an incline. I think this is actually a better example, so we'll kind of just stick with it. So redrawing this yet again. Yeah, we'll ignore friction for now. Alright, so this is M1. We have tension pulling it up the incline. Gravity straight down. We'll call this M1. And the normal force. Remember, normal force is always perpendicular to the incline. That's what normal means. So let me rename this M1G. And at least for now, we're ignoring friction because we have to start this way to determine which direction the cart wants to move. And then we could add friction to it. So we identified all the forces acting on both of the objects in our system, neglecting friction. Notice that there's two factors to consider. Well, there's usually only one factor to consider when it comes to picking a coordinate system. And that is the motion of the objects. So let's look at M1. We can pick our, let's say we do this. We pick our standard XY coordinate system like this. Now, could we do this? And the answer is yes. Do we want to do this? Definitely not. The reason why is this cart is moving, we can describe the motion of it with a single variable. But if we have our XY coordinate system like this, as it's moving up or down the incline, both the X and Y coordinates are going to be changing. So in this case, we want our coordinate system to be in the direction we expect it to move. Let's say we think it's going to move up the incline. So let's call that our X direction. And we'll call the perpendicular direction Y. Now that's a coordinate system for mass 1. And sometimes you just want one coordinate system and leave it at that. I can give you an example where we have two objects. And we're going to actually do this example, but for now we'll just write it down. This is something called an Atwood machine. So we have two masses, and let's say they're different. Let's actually give them numbers. Let's say this is 100 grams, and this one's 50 grams. And let's say we release it from rest, so we know this cart is going to move down, and this cart is going to move up. So there's two ways we could go about applying Newton's second law here. We can pick two coordinate systems. We can say this is y1 and this is y2 and just have a different coordinate system for each mass. That's perfectly fine. That's probably how I would do it in this case. But yeah, so let's say this is one way to do it. And I'm actually going to do an example of this Atwood machine. So I'll do it the other way. Another option is just to say up. is your positive direction, and have that coordinate system apply to both masses. So we'll do this example down the road. Okay, but in this case, we definitely do not want to apply the same coordinate system to both masses. So like this coordinate system is great for describing the motion of the M1 that's going up or down the incline. It's not convenient at all for describing the motion M2, which is just purely vertical, because these directions are, at that incline. And so for mass 2, I'm going to find mass 2 to be downwards, or the Y2 to be downwards for this system here. Because that's we have to make an assumption about which way. Let's assume that, the reason I'm assuming this is because we're into a lab where we actually use this, where typically we have enough mass here to lift the cart up. So if M1 is going to go up and M2 is going to go down, we'll define our coordinate system this way. Yeah, I want to make sure that that's all visible. Yeah, like what I can see on the screen does not match up with what's available in the video, but always makes me nervous looking at that. Can't see it. So right now, let's assume that M2 is enough. So M2 is going to fall down and drag M1 up the incline. Then we would do it this way. Okay. So now that we have all of our forces, then we picked a coordinate system. Step 3 is break forces into components. If necessary. Okay, so we've got two masses, M1 and M2, and M2 is not a problem. Like, we can draw a free body diagram for M2. Well, we don't even need to draw a separate object for M2, because we can see there's two forces, M2G, that would be the force of gravity, and tension upwards. So again, that picture is clear enough without drawing it as a separate object. But for M1, let's look at that. So we've got M1 here. And let's look at all the forces and determine if we need to break any of them into components. So let's look at tension first. Tension is in the x direction. We're totally fine there. So tension, we leave that one alone. How about the normal force? Normal force is in the y direction. So again, we're fine. We have no problem with either of those forces, but gravity is not in the x or the y direction. So gravity has to be broken into components. Gravity is straight down, but what we're going to do is break it into a component in the y direction and a component in the x direction. So I'm going to draw this. We've done this before, but we'll do it again because it's important to be able to break forces into components. So we have our incline. Say here's our mass, and we're just going to draw gravity, which is straight down. And then we have our XY coordinate system like this. And the incline of this slope is theta. Should make that angle theta. I'm also going to draw a horizontal line going through the center of our mass. So if this angle is theta, that makes this angle theta. It's at like alternate interior angles or something. And that would make this angle 90 minus theta, which would make this angle theta. So again, we'll review this in class when you have a chance to ask questions. This is a frequent source of confusion. So here we have gravity straight down. We're breaking it into a component in this direction, in the y direction, and one in the x direction. So a parallelogram here. And so this one in the y direction is adjacent to the angle. So this is mg cosine theta. And the other one is mg sine theta. Yeah, like in the x direction, this is opposite the angle, and so we use sine for that one. So now we've done that, I'm going to have to erase this picture, which is actually a good thing. I don't want it anymore. So, the last step here is apply Newton's second to each mass in each direction. Okay, so what this means, we're going to have three equations here. If we look at mass 1, we have things going on in both the x, let's call this x1 and y1. So we have things going on in the x1 and in the y1 directions. For mass 2, we don't have an x2 because we don't need one. We could draw it if we want, but nothing's going on in the x direction for mass 2. It's just going, purely vertical. And so, we'll have three equations. 2 for mass 1 and 1 for mass 2. And if you've done these first three steps, step 4 is actually easy. Or it should be anyways. So let's just look at the x direction. Like the key here is once you get to this step, we break forces into components if necessary. The end result is all of our forces are in the coordinate directions. So like gravity is, one force. We're treating it as two separate forces. Which, again, in our vector lab, we saw that forces do actually behave this way. That we can treat it as two separate forces. And so let's just look at mass 1. Here, mass 1. We're going to have two equations. So in the x direction, let's just look at these forces. There's 4 of them. Which ones are in the x direction? That's here. Tension and this mg sine of theta. Those are in the x direction. These two are in the y direction. So like once you get to this point, it should be very obvious what direction these forces are, like which ones are in each direction. So if we look at the x direction, when we picked upwards, like up the incline to be positive, so tension is positive, but mg sine of theta is negative. So the net force is T minus, this should be M1G, should have been the 1 there. So M1G sine of theta. And that's equal to M1A. So that's it in the x direction for mass 1. We have these two forces. Looking at our coordinate system, T is positive, M1G sine of theta is negative. So when we add them, we have a minus sign here. And so that's the net force, and that's equal to mass times acceleration, specifically M1 times A. Now in the y direction, we have the normal force, and that's in the positive y direction, and this is in the negative y direction. So we have Fn minus M1G cosine theta, which is equal to mass times acceleration in the y direction, which is 0. So, we're going to set that whole right side to 0. And then for mass 2, we have gravity and tension, and the way to find it, y2 is downward. So we have m2g minus t equals m2a. And so now, in a sense, we're done with this process. So what we do is we have Newton's second law. We've applied it to this problem, and we get three equations out of it. Sorry, 1 second. Okay, so yeah, we get three equations out of this. 2 for m1, 1 for m2. And now, that doesn't mean that we're done with this problem. Like, what we would want to do with this problem would be, like, find the acceleration of the masses. That would be one example. Or maybe find the tension in the string, or both. But just applying Newton's laws doesn't mean we have all the information that we need. So another step, like this is specifically how to use Newton's second law, so here, we're done with that. But there could be another step involved in solving the problem, like see if there's any other equations relevant to the problem. And one of those would typically be friction. If you have a force of friction is mu Fn, yeah, we might have to write that equation down as well. But this is the procedure for doing problems like this. And I think we'll do this in class, like during a review where there can be questions, and we'll actually solve for the tension and the acceleration. I just don't have room on the board to actually solve it, but this would be a good problem to do in class. But I want to do another problem, that Atwood machine, which we will solve. This one wouldn't be too bad to actually do. It turns out the second equation, we could completely ignore it. You know what, let's solve this while we're here. I think what we'll do in class is add friction. So since we're here, let's actually solve this. So this is our set of equations. I'm sorry, give me 1 second. All right, so I'm just going to write down these first two equations because that's all we need. So t minus m1g sine of theta equals m1a. And m2g minus t equals m2a. So we've gone through our process and figured out our equations, and again, we only need 2 in this particular case. Now, if friction was involved, we would need the normal force, so we would use that third equation. But since we don't need it, I'm not going to write it down. So let's just check one more time that I got that right. Okay, so that's good. Now, one thing I will say, you always want to be very careful in doing, plus and minus signs, getting that right. And I'll point out when we do that Atwood machine problem, I'll point out one potential mistake that's very easy to make. It didn't really show up in this problem, but in that one, very easy one to screw up. But let's continue. Now, this is a system of equations. Let's say we know M1 and M2. So let's say M1 is 500 grams. Let's say M2 is 100 grams. So we get a little smaller. And let's say theta is 15 degrees. So this is what we've got. And so we know M1, M2, theta, and obviously we know G. And so we Yeah, we want to solve for tension and acceleration. So, yeah, we have a 2 by 2 system. 2 equations, 2 unknowns. That's a good sign when your number of equations is equal to the number of unknowns. That doesn't mean that it automatically has a solution, but it's at least a good sign. And in this case, it will be fine. So there's a nice trick. What students like to do, because you learned it this way, is like a substitution method. You want to get rid of one of your unknowns. So the most common way to do it, like we could solve this equation for t, and say t is m1a plus m1g sine of theta, and then we could plug it in here, and then solve for the acceleration. Because we'll have one equation with one equation that only has one unknown, acceleration. But there's a much shorter way to do this. Exact same result, but let's just add the equations. So remember the goal when you have a system of equations where you have like unknowns, like a single equation with more than one unknown, you can't really do anything with that by itself. So you have to eliminate one of your unknowns, and if we just add these equations, t is going to be gone. So here, let's start with here. We have m2g, and then minus t, but then when we add this equation, we have a plus t, those cancel out. So here we have minus m1g sine of theta. So on the left, we have 4 terms. We add them all up. The t and the minus t cancel out. And on this term, or on this side, we have m1a plus m2a. Now we can clean this up a little bit. G times m2 minus m1 sine of theta equals a times m1 plus m2. And to solve for the acceleration, I'm going to write it in a particular way. And I like writing it in this form because we have 2 factors now. One is g, and the other just involves masses. Sine of theta, that's just a number, like sine of 15 degrees. You can plug that in and get a number. But, yeah, so like students very often ask, at this point, do we need to convert everything to kilograms because those are our basic SI units? No, we don't have to. Because if we just plug it in as it is, we're going to have grams divided by grams. That'll cancel out. So first, let's do m1 times sine of theta. So we do 500. Let's see, 500 times sine of 15 degrees, which is 129.4. So here we've got 9.8 meters per second squared. And then we have m2, which is 65. I'm going to leave the units off because we know top and bottom are both in grams. And then minus 129.4. And then we divide by m1 plus m2, that'd be 565. So what we're clearly seeing here is a negative acceleration. So is that bad? Not in this case. That's totally fine here. Because what that means, we kind of assumed in advance that this mass was going to be enough to, drag this larger mass up the incline at this particular angle, but that's not what we're seeing happen here. Yeah, I guessed wrong. And I kind of was hoping it would turn out that way. Yeah, we guessed wrong in this case, and so we get a negative acceleration, that's fine. So I'm just going to get a number. That fraction is about 0.11 and then times 9.8. So I'm getting an acceleration of minus, say, 1.1 meter per second squared. So all that minus means is it's accelerating down the incline instead of up. So in a sense, it doesn't matter how you pick your coordinate system. If you picked it wrong, well, you just get a negative sign. However, that's not always going to be the case, because in this particular problem, if we were taking friction into account, the direction that it's moving definitely is an important factor. And so if we made our guess, like if we added friction to it, we'd have to first start without friction. And when we see that this term is bigger than this one, then we would know we guessed wrong. And so because this cart's going to actually go down the incline, then we could add friction going this way. Like you have to know what way the masses are going to move before you can determine which direction friction is. So like once we found out that this coordinate system was kind of backwards, we just went with it because we're ignoring friction. But if friction was a factor, then we would have to, change our coordinate system around. Would probably be the best way to do it. Okay, but we know that the acceleration is 1.1 meter per second squared down the incline. So we solved that part. When it comes to tension, let's use this second equation just because it doesn't involve that sine of theta. So we can say T is equal to M2G minus M2A. Okay, so we can factor the M2 out. Okay, and then we can plug in our numbers. We have 65 grams. In this case, I want to convert to kilograms. So when we're converting from grams to kilograms, we divide by 1,000. And we know the acceleration. Now the question is, do we want to plug a minus sign in or not? So let's think about that. If we just held this in place, the tension would be equal to M2G. Like if that mass was just hanging there, but we're lifting it up, so we should expect the tension to be greater than that. And so we'd have M2 times G minus, we'd want to include that negative sign. So we have 9.8 plus 1.1, which is 10.9. And then, so 9.8 plus 1.1, or minus negative 1.1. So G minus A, that's 10.9 meters per second squared. And then times 65 is 709. Or let's round that off to 710. But then, we divide by 1,000. So the tension is 0.71 newtons. So here's the acceleration. Here is the tension. Okay, so that's how we do this problem without friction. And in class, we'll do a problem like this that does involve friction. Which again, it wouldn't be that we'd go through the exact same procedure, except like in this case, now that we know the cart's going downhill, we'd put friction going this way. At this point, I'd probably flip it around, so X is down the incline, Y is perpendicular. You don't have to do that, but that might be a little bit easier. Let's do one more problem, though. I want to do the Atwood machine problem. So let's clear this whole thing. Okay, so I'm going to draw an Atwood machine. Not the best circle, but use these numbers just like we had before. M1 and M2, 100 grams and 50 grams. So we know mass 1 is going to fall down and mass 2 is going to accelerate upwards. And they're connected by a string that doesn't stretch. And so they're going to, like if this mass falls down 1 meter, mass 2 is going to go up 1 meter. They're going to travel the same distance in the same time period. They're going to basically accelerate at the same rate. So what I did last time, because M1's bigger, it said like, let's say this is Y1 and this is Y2. And that's the way I would prefer to do this, because it avoids the possibility of making this, this mistake. But just to illustrate that, let's just pick our Y direction to be positive and apply that to both masses. And again, it's a totally fine way to do it. You just have to be careful. So let's identify the forces. We have tension and gravity. Okay, now let's look at mass 1. Up is our positive direction. So we have T minus M1G. That is our net force. And that's equal to M1A. Force is equal to mass times acceleration. Let me write down Newton's second law, actually. So, I mentioned we want to, well, let's move on, and then I'll point out the mistake here. Let's look at mass 2. T minus M2G equals M2A. And if we do this and carry on, this is wrong. Now, what's actually wrong with this? Well, I mentioned earlier that both masses move together. So they have like the same magnitude of acceleration. However, the accelerations are not the same because one's accelerating down and one is accelerating up. So the only thing that's the same about them is the magnitude of the acceleration. So we could do this way. Let's call the acceleration of mass 1 A1 and the acceleration of mass 2 A2. Now this is correct. And let's call A the magnitude of the acceleration. So A is the magnitude, and so we can say that A1 is equal to minus A, and A2 is equal to plus A. So like say A turns out to be like 2 meters per second squared. Then A1, because it's accelerating downwards, A1 would be minus 2 meters per second squared, and A2 would be plus 2 meters per second squared. Now, normally I wouldn't write this all out. I would just, when setting it up, the net force is mass times acceleration. I would just, instead of writing A1, just say minus A. And this one, I'm going to write plus A. You wouldn't have to write the plus there. And so now we have our correct system of equations. Where, let's say we did it this way. Let's say this is Y1 and upwards is Y2. I'm just going to write this down. I think this is a better way to do it. So the way I would set it up is M1G minus T equals M1A. And over here, so for mass 1, M1G is positive, T is negative. Because in this coordinate system, down is positive, up is negative. Here, up is positive, down is negative. So we have T minus M2G equals M2A. And we don't have to worry about the acceleration here because, they both have the exact same acceleration. And the coordinate systems we're describing them, both of the accelerations are going to be positive now. This one's going to be positive down, this one's positive up. We're going to get the exact same result as before. And this system of equations is exactly equal to this system of equations. They might look different, but if you multiply this top equation by -1, we'd have minus t plus m1g, which we could flip around, m1g minus t. Multiplying by negative 1 gets rid of that, and we have m1a. And the second equation we would just leave alone. So again, I think it's a little safer to try to pick your coordinate system so that things are accelerating. Pick your coordinate system so they accelerate in the positive direction, and then you won't have this problem. You also won't have the problem if you set it up correctly, but it's easy to overlook that. So now to solve this, let's call this equation 2. Here, this equation 2, I'm not going to write down because there's no room. Here's equation 2, here's equation 1. So let's do equation 2 minus equation 1. And the reason why, if we take this equation and subtract this one, we'll have t minus t, and they'll cancel out. So if we're subtracting this, we'll have m1g minus m2g, and we're doing the second minus the first. So that'd be m2a, and then minus a negative, we're going to have plus m2a. And again, we can factor a g out and factor an a out here, which I did wrong. Well, it doesn't. Here we have m2a plus m1a. Doing this minus that. And so m1 plus m2. And our acceleration would be g times m1 minus m2. So that'd be 50 grams over m1 plus m2, which is 150 grams. And so that'd be 9.8 over 3, so like 3.3. So that would be the Atwood machine. And again, just always be careful with these plus or minus signs. And yeah, we'll go over more examples in class because, this is kind of like the crux of it, using Newton's laws. It's easy to state Newton's laws, but we have to learn how to use them as well.